So we have discussed about two cases in variable demand. So the first case is the extreme case where the rent cost is much larger than the inventory waiting cost. So in this case, we have identical shipping loads, so we can have a closed form. And then in the second extreme case, we consider the inventory waiting cost is much larger than the rent cost. And then in this case, we do not have a simple method to solve, but we develop some interesting algorithm. So for example, we have this shooting method and also our dynamic programming algorithm. For a general case, where the inventory waiting cost and the rent cost are to be considered at the same time, then the problem becomes much more difficult. Typically, there's no simple way to get a closed form. In this case, we will try to extend the dynamic programming method and then develop an efficient algorithm to solve the general case. So recall in the extreme case where the inventory waiting cost is much larger than the rent cost, so our problem is reduced to optimize the shaded area given a certain number of shipments, or jointly optimize the number of shipments and the shaded area together. So in this case, if we do not have the conditions that the inventory waiting cost is much larger than the rent cost, we have to consider them at the same time. So in that case, the load each time we ship is related to the rent cost. So remember, in our dynamic programming algorithm, we introduced the decomposable problem. So that means when we have the entire problem is optimized, then each subproblem is optimized. But here, when we consider a general case where the rent cost is considered, the general problem is no longer decomposable. So for example, let's see if this is an optimum solution. So let's consider a subproblem. So when we try to solve this subproblem given a certain parameter of the unit rent cost, then it's hard to solve the subproblem without knowing the information outside this subproblem. The total rent cost is determined by the capacity of the rent space. Let's see if at time t0, t1, t2. So if the load at t0 is much larger than the load at t1 and t2, which we denote them by v0, v1, and v2 at respective time step, then when we try to solve this subproblem, you can see the rent cost will not be changed. When v1 and v2 changes, the rent cost does not change. So this causes a problem because when we try to solve the subproblem, we need to consider the rent cost, but when we try to adjust our decision variables on our schedule, our rent cost will not be affected. So if we don't know v0, when we solve the subproblem, we cannot tell when the rent cost will be affected. Definitely if v1 and v2 is greater than v0, the rent cost will be changed. Right, so the rent cost will remain if v1, v2 is smaller than v0, and then the rent cost will change when v1 or v2 becomes greater than v0. So without knowing the information of v0, we cannot calculate the rent cost for this subproblem. Okay, so that means this problem is no longer decomposable. We cannot immediately apply the dynamic programming algorithm. So to this end, how should we extend the dynamic programming to solve this problem? As we mentioned, the load doesn't matter. No matter what kind of subproblems you solve, we have to consider the condition that the rent cost will change. So in this case, we can assume the capacity in advance. Okay, so that means we assume a Vmax, and then we will adjust this Vmax gradually. For each possible Vmax, we can solve a certain decomposable problem. So let's see why. So if we assume a Vmax, then whenever we try to solve the problem, so all this load, let's see, T0, T1, T2, V0, V1, V2, we guarantee that V0, V1, and V2 has to be small or equal to Vmax. And then our run cost can be approximated by CR Vmax. This is our load times the time, Tmax. Okay, so whenever we have this assumption on Vmax, we can estimate the run cost explicitly. And then as long as we guarantee that each load size is smaller than the Vmax, the problem actually is reduced to the previous dynamic programming problem with a constraint. So let's see how we reduce it. Recall that in the previous problem, we can decompose from T0 to T1, and then we can have a subproblem at T1. So that means our subproblem from T0 can be written, the Bellman equation, right, can be written as minimize T1 such that we have this one-step cost, or we just say one-step cost from T0 to T1, and then plus the subproblem from T1. Okay, so here, if we assumed a capacity, so that means we just consider a capacity here. So whenever we try to design our dispatch, we will guarantee that the load here, this is V0, we guarantee that Vmax is greater or equal to this V0. This can be easily achieved because when we enumerate possible T1, we just guarantee that the load we ship from T0 to T1 is smaller or equal to Vmax. Actually, this is very easy to estimate it. V0 actually equals to D at T1 minus D T0. So that means we can just change the condition. Because the cumulative demand function is an increasing function, we can know that the value for dt1 equals to Vmax plus dd0 is easy to get from the enumeration.